Hi everyone and welcome to this tutorial. As you might know, with the release of Spring Boot 3, the sloth library is no longer used. In this video we will talk about new tool, Micrometer, and then build a project with multiple microservices where I will show you how to implement distributed tracing from scratch using Micrometer and Zipkin. But first, let's talk about what distributed tracing is and why it's essential for the microservices. I will use an example to make it clearer. Let's say we have an e-commerce project with the microservices like payment service, cart, user service, and inventory service. All these services may call each other. For instance, when a client wants to pay for an order, he sends a request to the payment service, and the payment service needs to get information about the user, retrieve the items from the cart, check with the inventory service if there is enough stock, and finally process the payment. Now let's imagine that one day your manager informs you that the system has started slowing down and clients are getting frustrated. What would you do in this situation? Well, naturally, you'd look at the logs, but with so many client requests spread across multiple services, it becomes nearly impossible to correlate logs across services for any single request. This is where tracing becomes invaluable. Tracing allows us to follow the life cycle of a request as it moves through different services by marking it with the unique identifier called trace ID. This trace ID stays with the request while it travels across all microservices, and more than that, each microservice adds its own span ID to uniquely identify its log entries, helping us to trace the exact path and timing of each request. If you have never heard about tracing before, it might seem a little confusing, so let's go back to the example and see how it works. When the request from the client reaches the first microservice, the payment service in our case, it will check if the request has trace ID headers. If not, it generates one. After that, any request the payment ID service sends to other services will carry the same trace ID. And each service, including payment service, will add its own span ID, which lets us to group logs within each service by request. Okay, now to demonstrate how to implement distributed tracing in Spring Boot 3, let's create a new project. In this step, we're going to create a new Maven project that will serve as a root and then add 4 modules that will represent our 4 microservices. The name will be Zipkin Tracing Demo. Type Maven, Java 21. And this root project will remain empty without any dependencies. We also don't need the src folder here. The next step is to create internal modules. First, let's create a payment service, Maven, Java 21. Next, and we also need to add 3 dependencies, actuator, Spring Web, and Lombok. Now create. And next the cart service. All settings will be the same. And dependencies will be the same too. And now user service, Maven, Java 21, actuator, Spring Web, Lombok, and finally the inventory service. Okay, with that, our basic multi-module Maven structure is ready. Now let's move on to configure each microservice module with the necessary dependencies and initial setup. First, we need to add new modules to the pom.xml file. I will clean up unnecessary lines and add the modules block here. In this block, we need to list all our modules. And since we're not planning to write tests, I removed this section. Now let's set up our root project as a parent for all internal modules. To do that, we need to add the same group ID, artifact ID, and version to each internal pom.xml file. I will start with the cart service. fill the parent section. Also remove unnecessary lines. Next, I'll do the same for the inventory service. Now payment service. Fill the parent section. Clean up unnecessary lines. And finally the user service. And it seems I forgot to specify the packaging. We need to set the packaging to POM here. Now there are no errors. Let's move on to setting up each application properties file. We don't need a test package. And we also don't need static folders in the resources. First, I'll switch the file type to YAML. And we need to specify only the server port for now. Port will be, let's say, 8081. And now do the same for other modules. Rename application properties. Replace the name by the inventory. Port 8082. Now the payment service. Clean up unnecessary packages. Rename application properties. Port 8083. Name payment. And finally the user service. Rename application properties. Name user and port 8084. So with it, the initial setup is done and we are ready to implement controllers. First, I'll create a controller for our main microservice, the payment service. We will have a single method here, which will return payment details. The only argument we need from the client here is invoice ID, and client will pass it as a path variable. Let's set getMap annotation and define a path. The method will produce JSON. Now let's turn out our class into a bin using the REST controller annotation. I want to keep the controller simple, so I'll move all calls to other microservices to the communication service. We also need the required args constructor annotation. Now let's continue with our method. Here I want to get the invoice sum. And user identifier. And then make a reservation of goods using invoice ID and user ID. If the goods were successfully reserved, then we would create the payment details object. I also want to log it, so let's add the self4j annotation and log the payment details. Now that we know the interface, let's implement payment details. Here we need invoice ID, user ID, and sum. I will also add getters, setters, and toString annotation. And we also need an indicator that shows the request was processed successfully. And finally, I will implement the reserve method. If the goods weren't reserved, we will log that. And then return the same result, but without success log. Now let's create the communication service. And first I will implement the getInvoiceSoon method. This method will call another service, so we need an HTTP client. Let's annotate the class with the service and required args constructor. Now we can declare the REST template as a private property and it will be auto-wired. But we also need to declare REST template as a bin. I will add it right to the application class. Now let's go back to the getInvoiceSoon method and complete it. We will pass invoice ID as a method parameter. And inside of the method we need to build URL for calling card service. And invoice ID at the end. Then I'll call REST template and return the result cast to double. Similarly, I will create the getUserID method, also build URL, for simplicity, let's assume that user service knows user ID. From headers, maybe it doesn't matter. And we only need to ask for user ID without passing any arguments. Then I'll call the service and return the result as alone. We will pass invoice ID and user ID as arguments, build URL for the inventory service, with invoice ID and user ID as the path parameters, and return the Boolean result. Now it's time to implement other controllers. I will start from the beginning and create the card controller first. Just annotate it with REST controller and define a single method, getSoon, with the invoice ID path parameter. I log the invoice ID right there. And then create a random double with 2 decimals. Log it. And return. Let's move forward and create inventory controller. Add the REST controller annotation. Define getMapping section with 2 path variables, invoice ID and user ID. Produce application JSON. Method will return Boolean. define the arguments, add self-for annotation. First I will log the input parameters. Then we just need to return a randomly true or false value. I will also log the result. And finally, user controller. And rest controller annotation and self-for annotation. It will have a single method without any parameters. Method will return user ID as salon. I will only log the user ID here. And of course generated before. Now that we're done with it, let's start our services and check if everything works fine. I have already prepared the request in Postman, so let's send it and then check the logs. I'll expand the window to make it more convenient. Now what do we see? Just log lines, nothing special. But let's say all these requests are sent by different clients, and for any reason we need to trace the requests and logs to see the correlation between the requests sent to all our services. So how can we do that? Our requests don't have any common identifiers or anything that allows us to trace them. Yes, in these two rows we have the user ID, but in the other rows we don't. Well, obviously, to trace requests, we need to mark each our request with the unique identifier and then pass it across all our services. The Micrometer tracing library will help us with that. Let's move on and add the necessary dependencies to all POM.xml files. We will need the Micrometer tracing dependency, which provides an API for collecting metrics and traces. Then Micrometer tracing bridge Brave, acting as a bridge between Micrometer and Brave. Zipkin reporter Brave is responsible for sending the trace data collected by Brave to the Zipkin server. Brave instrumentation Spring Web, integrating Brave with the Spring Web to automatically generate and propagate traces in web requests. Then simply copy this to the other modules as well. Now we need to configure tracing in the application YAML. I will add the section management, then tracing, enable true, and Zipkin tracing, enable true, and base URL with the URL of our Zipkin service. And then also copy it to other modules. Additionally, we need to replace the default REST template with the instrumentated one. I will use REST template builder for that and just call build. Of course, we need the Zipkin service. I will run it using Docker, but first let me add the Zipkin compose file. We need to add a single service here. Name will be Zipkin. Image open Zipkin /Zipkin, container name Zipkin, and also specify ports. Now let's get Docker and our services running. and then send the several requests. After that, we will be able to see the result in the Zipkin. Zipkin should start on the port 9411, and yes, it has started. We can now see the latest queries. Click Show on the first one. Here you can find an internal queries with the timings and other trace information such as trace ID, span ID, duration, and other. We can also go to the dependencies page and see the visualization of the request routes, and that's it. Okay, now I also want to show you something else. Let's go back to the first page and check the queries for that. If you were paying close attention, you recall that I sent more than 3 requests. Let me try sending more now. As you can see, only one new request showed up. So why aren't we seeing all of them? Well, that's because Zipkin isn't meant to trace every single request by default. On the production environment, tracing every request could impact performance and overload the Zipkin server. It's not designed to handle that kind of heavy load. As usual, tracing a small number of requests, whether it's 1 or 10 persons depending on your needs, should be enough. But sometimes, especially during the development or testing stages, this approach may be not convenient. When you test a new application, you might want to trace every request, and it's easy to do that by increasing the sampling rate. So, to do this, I will declare a new bin of type sampler. There are 3 options. Never, which means sampling is turned off. Always, meaning all requests will be sent to Zipkin. And finally, you can specify percentage, choosing value between 0 and 1. For example, 0.5 means that 50% of requests will be sent to Zipkin. Let's start by choosing always. If I restart services and send 1, 2, 3, 4, 5 requests, we can now see that all of them have appeared in Zipkin. Now, I want to dive a little deeper into a question you might be already asking yourself. If the sampling ratio is less than 100%, how do all the services know when they need send tracing data to Zipkin and when not? How are they synchronized? The answer is the first service that generates the initial trace ID also decides whether or not send the tracing data. It then adds the special flag to the request headers. Other services check this flag in the headers and use it to stay synchronized. Now let me show you how it looks. First I will change the sampler value to 0.5. It means that 50% of traces will hit the Zipkin. Next I will add headers to the getSoon method. It will be a map with the string keys and values. Restart in the debug mode. I'll also restart the payment service since we updated the sampler settings. Now send a new request, and let's see the headers and the breakpoint. Here is W3C headers, which is used by default. The final element in the string is the sampling rate. Now I send the next request, and we can see that the sampling rate value has become 1. Here is the specification of the W3C headers format. Header value is the string with the multiply sections separated by a dash. First section is a version. The current specification assumes that the version is set to 0. Then we have a trace ID, followed by a span ID, and finally the sampling state flag. The sampling state can be 0, meaning that tracing data isn't collected, or 1, which enables the sampling. And depending on our needs, we can change the headers format. Let me show you how. I will go to the application YAML of the payment service, and here I need to add new section, propagation, and set produce section value as B3. Then I will restart the payment service and send the new request. And here is what we got. The sampling flag here is set to 1, which means the tracing is enabled. Now I'll send one more request and we can see that the sampling flag has changed. And let's check out the specification. The B3 header is quite similar to W3C. The header name changed to B3 and we gain a new section named Parent Span ID. Apart from that, the differences are minimal. And finally, let's change the produce value to B3 multi and restart the payment service. And send the new request. As you can see, it's almost the same as the B3 headers, but split into separate header fields, just like in the specification. Each header name begins with the x-b3 prefix. Here we have trace ID, span ID, parent span ID, and the sampling rate. And now is a great time to remind you to subscribe if you enjoyed this video. In the next video we will explore how to configure and use another popular tracing and logging stack, OpenTelemetry with Jagger. And now, thanks for watching and see you in the next video. Bye!